Okay, good morning, everyone. Soon start session. Share the screen first. Okay, so in the last class, we had seen the 6 postulates for the process, and using the postulates and fairly elementary probabilistic arguments, we had seen that P0 of T, so that is probability NT equal to 0, that is the notation here. So that is given by e to the power minus lambda t for all t greater than or equal to 0. Using, of course, this initial value, so to say. So today we will look at what happens to Pn. So for n greater than or equal to 1, the integer, P sub n t plus h, which by definition of this Pn is probability n of t plus h equal to n. So this event were to occur, we are splitting it to 3 possibilities. All the n events have occurred before t or before or up to t, and in the interval t to t plus h, it is 0. Nothing, no event, no arrival in this interval, t to t plus h. Another disjoint possibility is that exactly n minus 1 arrivals have taken place in 0 to t, and exactly 1 arrival during t to t plus h. And another possibility is that in this, it is t to t plus h in this interval, there is 2 or more arrivals in such a way that the total arrival up to t plus h is n. So the disjointness, this is based on whether t to t plus h, it is 0 event, 0 arrival, 1 arrival, or 2 or more arrivals. Okay, it's, I suppose, fairly clear that there is no error in this. No, note it down if you want. All right. So now we will look at this term, the third one on the right side first. And of course, it is clear that in this thing, we are going to make use of that n5, n6, etc. So first, we write it as using the time homogeneity. We will, okay, before that, this is the intersection of 2 events. N of t plus h is equal to n, and this greater than or equal to 2. So probability of this intersection is certainly less than probability of just this event alone. So this less than or equal to, we are not using any of the hypotheses, any of the postulates. Now you use n4, that is stationarity. So this probability is same thing as probability n of h strictly, greater than or equal to 2. And by our n5, this is equal to small order h as h goes to 0. In other words, the contribution of the third term for small values of h is going to be very, very negligible. Because finally, we will be letting h go to 0. So verify that. Coming here. So this is just that step in the earlier slide. We have repeated up to here. And then the third term we had just now seen, it is small order h. So now the first term on the right side as well as the second term on the right side, you use the independent increment property. So these things concern events in the interval 0 to t and t to t plus h. So they are disjoint intervals. So it is this probability of this intersection is the probability of product of these two probabilities. Probability nt equal to n multiplied with probability n of t plus h minus nt equal to 0. And similarly here. And now you use the property of time homogeneity, that is stationarity of the increments. So this probability is same thing as probability of nh equal to 0. And this probability is same as probability nh equal to 1. So now this term here is precisely p sub n of t. And the probability nh equal to 0 by your n6, or both these things, n5 and n6, it is, so this is going to be 1 minus probability nh equal to 1 and minus probability nh greater than or equal to 2. So then you use this n4 and n5 and n6, then you get that is equal to 1 minus lambda times h by n6. Probability nh equal to 1 is lambda times h plus small o over h. So that, and similarly, this guy here by definition is p sub n minus 1 of t. And this is equal to this one. And of course, there is a small order h term coming from here itself. So note it down and also check that we have not made any silly error, typographical or logical. So please note it down. And also verify. See, all these things, note that, observe that, it is easily seen that these are all euphemisms for verify that. Those are dangerous statements when you come across in mathematics books and things like that. All those things would be small exercises so that while checking that, one gets to understand things better. Okay. So again, you can verify that. So this is here PNT into 1. So that is to be PNT. So that alone you take it to that left side. If you do that, all the other terms involve H. Involve H or small order H. So divide both sides by H. After bringing this guy from the right side and dividing by H, then you will see that this H gets cancelled and this H gets cancelled. So now if you let H go to 0, this last term vanishes and these guys are independent of H, so nothing happens to them. And this becomes the derivative of P sub n at T. So the derivative of Pn at T is minus lambda times Pnt plus lambda times Pn minus 1 of T. For any T positive and n varying over 1, 2, 3, etc. So please note it. So note that here we have a system of ODEs. Kind of recursive system. Now, if you put n equal to 1, n minus 1 is 0. So P0 of T we know. So then this becomes the equation for P sub 1 and so on. So to make things simpler, so to solve the above system of ODEs, of course, effectively, introduce this Q sub n equal to e to the power lambda T times P and T. Then if you differentiate or Qn, one gets, and using this equation, one sees that we get this equation. The derivative of Q1 at T is lambda times Qn minus 1. So denote this differential equation by dagger, or rather the system of differential equations by dagger for each n. So in principle here, you know P0, therefore you know Q0. So Q1 you can get from here And once you get Q1, you can get P1. But of course, at every time, you will have a constant of integration to sort of reckon with. Okay, so please note it down.
So, how did we get this thing? D by dt of q sub n t is equal to lambda times.
You differentiate this with respect to t.
Okay.
Then you get lambda times e to the power t times pn plus e to the power lambda t times.
Okay.
And then use.
Then the previous equation, that we had the relationship. Okay.
Yeah, good. Ask some questions like that. So all these things I expect you after you go back home. Rather, of course, now you are all staying at home, I suppose. You after the class, please verify each and every step. That's why every time I insist on using verify that. One doesn't expect you to verify then and there now. But one has to. And similarly, in this sequence of steps, please verify each and every step carefully. Say sometimes while typing, this thing that one makes some errors. I might have copied up to or typed up to this correctly, and then from my notes or handwritten this thing on a piece of paper to transferring it here, something will get mixed up. Yeah. So I hope it's fairly clear how to go about verifying this. So please do that. Don't postpone it. Such things. These things will suddenly accumulate. So note that Q sub 0 from when you put n equal to 0, since we know this P0 and so on, is identically equal to 1 because we already know P0t is e to the power minus lambda t. So this equation becomes the derivative of Q1 equal to lambda. So which means Q1t is lambda t plus a constant. So that constant we have to find using the information we have concerning the initial value. So what is Q0 of 1? It is precisely when you put t equal to 0, e to the power e to the power lambda t is just 1. So Q1 of 0 is same thing as P1 of 0, which is by definition of our this P sub n, it is probability n0 equal to 1. But we know that n0 equal to 0 identically. So therefore probability n0 equal to 1 is 0. Consequently, one gets that this little c is 0. So Q1 of t is lambda t. For every t greater than or equal to 0. Note it down. Just excuse me, somebody seems to be at the door. Oh, I'm sorry. No, Sundar might have told you that yeah. Yes, we need to for one more thing. And supposing by on its own. Thanks a lot. I'm happy class always. Yeah, sorry for that small distraction. So Q1T is lambda t. So next for n equal to 2. So similarly, you can see that the derivative of Q2 is lambda times Q1T, and we now have Q1 information on Q1T. So therefore, it is lambda squared times T. So one easily gets that Q2 is half lambda squared T squared plus a constant. So as before, to evaluate, to find what this constant C is, one uses the information P2 of 0 is probability N0 equal to 2, and that is 0 we know. So one gets this little c is 0. So Q2 of T is half lambda squared T squared. So as one proceeds further, at every time you will be integrating such a quantity. So it is clear that these powers of this will increase, especially this one. And also you expect something to come also in the denominator without this getting destroyed. So therefore, one expects those things will accumulate. So 2 you can write as 1 multiplied with the 2, so 2 factorial. So that is the kind of guesswork here, that what is going to happen. So that is why we are writing like this. So you can now try to easily guess a formula for Qnt and so. Please note it down. So therefore, we guess that Q sub n t is going to be 1 divided by n factorial multiplied with lambda power n t power n for t greater than or equal to 0 and n equal to 1, 2, 3, etc. So denote this system of equations by double dagger. So since we have got the guesswork done here, but our objective is to show that this is satisfied for every n. So one verifies that Qn given by this solves the equation, the system of equations dagger, of course, using induction on n. And with the initial value, Qn at 0 is equal to 0 for every n greater than or equal to 2. Of course, another thing to assume is that you assume that this formula holds for up to k equal to, n equal to k minus 1, and then verify that when k equal n equal to k, also you get this as the solution. So we get the following result. So if you want me to, so what we have given the proof now. You want me to go through the series of the slides? I can do it before we state the theorem.
No, sir.
Okay. So instead of stating the theorem and giving the proof, I thought in this case it would be better if the proof is given. That will tell you one way of arriving at this result. So let the counting process Nt satisfy the hypothesis N1 to N6. Then the result says for any t greater than or equal to 0 and s greater than or equal to 0, probability n of t plus s minus ns equal to k, by our assumption n4, that is time homogeneity or stationarity of the increments, this probability is same thing as probability nt equal to k. So probability nt equal to k in our notation is pkt. So pkt is e to the power minus lambda times qkt. And that is what qkt, we have the formula. So you get probability nt equal to k is 1 over k factorial times lambda t to the power k multiplied with e to the power minus lambda t for k equal to 0, 1, 2, 3, etc. So here again, you have to check that we have actually proved this theorem, because see this equality follows by n of assumption n4, and this follows by our having evaluated qk. So you have to please check these things, that I'm not pulling a fast one on you. Now you see the right hand side is an object that you will recognize immediately. It is the probability mass function of the Poisson distribution with parameter lambda t. So the random variable for every t greater than or equal to 0 or t greater than 0, let's say, the random variable nt has the Poisson distribution with parameter lambda t. And therefore, the stochastic process nt, the continuous time stochastic process nt, is called a time homogeneous Poisson process with arrival rate lambda greater than 0. Okay, so I want to make some comments. Okay, first you see this. So the time homogeneous Poisson process with rate lambda is basically a counting process, of course, satisfying this n0 equal to 0, nt has independent increments, and the number of events in any interval has length t as a Poisson distribution. In other words, what one wants to say here is that if you assume that you have a process with this counting process nt, which has this property, then it will satisfy all the hypotheses. I mean, assuming that hypothesis n1, n0 to n1 to n6 is equivalent to these things. The counting process such that n0 equal to 0 is just n1 and n2. So this is n3 independent increments. And this is same thing as n4, n5, n6. Okay, this is just a very small comment. But what I want to point out is go back to the hypothesis. Yeah. Well, n1 and n2, n1 and n2 are basically that it is a counting process. So there can be any number of counting processes, perhaps. This is a very important assumption. This is again independent increment property. This is time homogeneity, that is stationary increments. This assumption is not very important. I mean, rather, we can relax this. If we relax that, then in n5, okay, n5 will again be same, negligible probability of 2 or more events in a small time interval. Here we'll have to make a change that this lambda cannot be taken to be a constant. It will be a function of a t and so on. So that can be, we will see later. In other words, in these postulates, there is nothing quantitative being assumed. all are basically qualitative kind of assumptions. Fairly general assumptions. That's what one means to say. Basically, a counting process with independent increments, and the probability of two or more events in a short span of time is negligible. However, the conclusion of the theorem is something very, very specific, quantitative. That under these assumptions, that kind of process has to be the Poisson process. Very, very specific. So that is why Poisson process or Poisson distribution you come across in many places. When you did probability course, that would have been introduced as a kind of approximation for the binomial probabilities, when that n times Pn goes to stabilizes if it converges to a limit, let's say lambda. But that looked rather contrived, that kind of justification for Poisson, importance of Poisson distribution. So the main reason, real reason is it occurs because of this result. A similar result you have come across, that is, assumptions are fairly qualitative, but the conclusion is very definite. This is the central limit theorem. You have IAD random variables. I mean, I'm talking about just that there are various generalizations of central limit theorem, but you have seen that Lindeberg-Levy IAD random variables such that the variance exists and so on. Then if you take that normalized sum, that it converges to a standard normal distribution. And that is the reason why you come across normal distribution in many places. And also that plays a central role in statistics. We are able to make statistical conclusions and predictions from limited data. And the underlying mathematical reason is that many of this kind of situations are governed by a Gaussian law. So that is why that distribution is called normal, as if other things are not normal, abnormal. So these are the normal distribution and Poisson distribution. These are distributions which you crop up in many places, in many disciplines. And many other distributions you see also might be related to these things. A geometric distribution, you know, it is the waiting time for first success and so on. And soon we will see exponential distribution also coming up here. Okay. So that is, so please note it down. So the result, or rather the importance of Poisson distribution and rather Poisson process, or rather Poisson distribution is due to basically Poisson process. And that we have derived it. And the derivation is pretty simple. Probably it doesn't require a lot of tools, unlike the proof of central limit theorem. Yeah, this is what I was. The assumptions N1 to N6 are basically qualitative nature. However, the result of the theorem, the main conclusion is quantitative. So some of the places, this is a very famous kind of experiment due to Rutherford about more than 100 years back. So say NT is the number of radioactive disintegrations detected by a Geiger-Müller counter during 0 to T. So there it is observed that that number, it follows a Poisson distribution. As a matter of fact, the chi-squared fit for the distribution is listed in Feller's volume 1. That's very famous, the result of that famous experiment due to Rutherford, and which led to the atomic theory of that. I mean, that is the nucleus is at the center and surrounded by electrons going in orbit and things like that. So the rare event, that is 2 or more radiations in a small interval of time, the probability is negligible. In many such cases also, you will, if you look at Feller's book, there will be a lot of such illustrations. So in this case, one of the basic assumptions you should make is the half-life of the substance, since it's a radioactive substance. So when the amount of radiation becomes half, that time period. So that time period should be considerably larger than the relative to time scale you are using here. Usually this half-life for, let's say, very higher order metals, which exhibit this thing, or even carbon, will be in the matter of hours or sometimes days, and in case of certain objects, it may be a number of years. So that is very large compared to this time scale T, which will be in terms of seconds or microseconds and so on. And another instance where this occurs, number of shocks received by a system during its course. And of course, the assumptions that the multiple shocks do not happen in a short span. So there are also things called shock processes and things like that, and various manifestations. That is how these things can affect the system. Sometimes a particular system becomes dysfunctional if there are, let us say, certain number of shocks. Each shock can damage partly, and if the shock exceeds a certain number or beyond a certain threshold, things might fail. And in this thing which is, this is a kind of, okay, let me first say, NT number of customers arriving at some service counter, maybe at a toll gate, or earlier we used to have that railway booking counter, railway stations. Those were a very famous example. And a number of telephone calls at a telephone exchange. So that kind of an example is introduced in Feller's book in the context of Poisson distribution. So generally, where you consider this kind of situation, that comes under what is called a queuing theory, and that is a big subject in its own right. Many situations which arise in applications of probability can fall in this category. So you can consider these things are basically three classes of examples. So this is a fairly large class, and so are the, and of course there are some similarity between this and the other one. And this is, of course, this also lead to some spatial, Poisson point process and things like that. We will not go into it. And many useful and interesting quantities can be obtained fairly explicitly in the case of Poisson process. That is, the distributions of those things can be obtained. And some of these things we will take up from the next class. We will first find out the waiting time distributions. That is, this is a counting process, and this NT denotes the number of arrivals or number of events of interest during 0 to t. What is the time of arrival of the first event? The time of arrival of the second event, and things like that. And you will see that such things one can compute find fairly explicitly. So that we will take it up in the next class. If you want me to go back to any of the slide, please tell me. I can do that. Or any questions?
Just one question. Which book would you recommend for problems?
See, there are several books. So, and certain these are, for example, the Sheldon-Ross stochastic process is one thing I have recommended in the list. Then I think, see, Hoyle, Porter, Stone book on stochastic process has some information, but that is unlike the case of Markov chains, it is in the chapter called Markov jump process. So that deals with the more general kind of process than Poisson. And also some things will be there in many applied probability books. So these are, and then of course, Carlin and Taylor. Carlin and Taylor, again, Poisson process is discussed in what is called a continuous time Markov chains. We will do continuous time Markov chains, but there it is a kind of example of Poisson, the Poisson process. But then again, there are a lot of problems concerning that. Then Sheldon and Ross, there is also a book called Probability Models. That is more elementary book. So some of these books, I will tell you some more list, but this might have been taken from various sources, or rather it is, what is it? That might have been, saying this thing might be inspiration from coming from various sources. See, I have written one book on insurance models. There also you will find some these things, but then that assumes quite a bit of measure theory. So it is it is little in various, and then there is a famous book by Asmussen called Applied Probability and Queues. And I don't know how many of these books are available on the net. That is another problem. Okay. See, last time when I taught analysis 3, fortunately for us, there was a very new book which was readily available on the net, free of charge, that NAPS book. And last semester, that Hoyle Port and Stone, which we used as a kind of main book, there again we had also used Sheldon Ross and so on. Again, see these things, I don't know how to what extent they are available on the net, because these are old books. Sometimes they may be available, sometimes they may not be. So that is one difficulty. I mean, had it been that the classes been offline, no, then you could have used the CMI library for many books. By the way, I saw a notice from Professor K.V. Subramaniam that between 12th and 28th, some students can move in to campus.
Yes, sir.
So I don't know how many are expected to move in. Anyway. So anyway, these are kind of that the the situation is like this. So we have to sort of work within these parameters. If you have access to any book on applied probability and things like that, take a look at that, might give you some ideas.
Okay, thank you.
I will also send you a list of, problems
Okay.
as usual. So that is, and I also try to give fairly detailed notes. So hopefully that will also help. Okay, so we will end the session now and meet next class.
Thank you, sir.
Thank you very much for your patience.
Thank you. Have a nice weekend.